All right. Well, hello and welcome to everybody. I can see a lot of folks are still joining the call. But before we really even kick off, we've got some things to go over. So we're really excited that you guys could join us here today to hear about one of the coolest space programs that's being worked. And before I kick it over to our speaker, Darnell Dixon, I do want to cover a little housekeeping items. We are going to play a couple videos today. So if you aren't joined via Zoom on your computer or iPad, you will want to join for audio purposes to hear the videos best from your device. Closed captioning today is available. If you need it, you can click on the little CC button at the bottom of your screen. If that is not working for you, there is a link to the closed captioning in the chat box. So today, all of the attendees who are joining are in listen-only mode, but we will be monitoring Q&A throughout. So if you do have questions for our speaker or anything about the presentation, then please use that Q&A feature to ask your questions. We're going to go ahead right now and test that. So if you are sitting at your computer and you can type in a question, go ahead and type in where you're calling from. And if you're a student, let us know what school you attend. So while we look for those questions to come through, those question tests, the last item to go through is that for everybody's awareness, member of the media may be present on this call. So I see some students from all over: Canyon Woods Middle School, New Century Technology High School in Huntsville, Alabama, Los Angeles, California, Sutter Middle School. Very cool. So we've got lots of folks on the call today. All right. So today I'm pleased to present our speaker, Darnell Dixon. And I'm actually just going to ask Darnell if he will go ahead and do an introduction for himself. Darnell?
Good afternoon, everyone, and thanks for joining in. Again, my name is Darnell Dixon. I am 36 years old. I was born in Anchorage, Alaska, and raised in the great town of Dinwiddie County, Virginia, the real DC, for those that don't know. I graduated from the Virginia State University, where I earned my Bachelor of Science in Electronics Engineering. And I currently am a manager here at Northrop Grumman in the Tactical Space Systems sector, where I manage a lab of 22 technicians. And in our lab, we perform environmental testing on the electrical components of the satellite before they're integrated onto the actual satellite. I have been here for 10 years, and it has been very fun, interesting, being able to work with NASA and other space customers. Next slide, please. As you all know, today we're going to talk about going to the moon. And the first thing that we're going to discuss is who is going to take us there. I'm sure you all heard of NASA, the agency in charge of science and technology that has to do with space. So NASA has a lot of programs they work on, and there is so much work to be done on these programs, and they need to hire additional people to support their teams. So that's where NASA partners come in. And these partners are government contractors and other commercial and international companies that NASA hires to work on certain programs. Today, we're going to talk about one specific NASA program, Artemis, which is the program focused on landing humans back on the moon. Specifically, we're going to cover some of the areas of Artemis being worked on by one of NASA partners. And I'm sure you want to know what that partner is. It's Northrop Grumman, of course, and that's where I come in. Next slide, please. Artemis, if you want to know what it is, which I'm sure you do, is a twin sister of Apollo, the NASA program that resulted in America's astronauts making a total of 11 space flights and walking on the moon. This time, though, with Artemis, wasn't the first woman to the moon. All so that we can study even more of the moon's surface and use new information and science to help us take our next giant leap and send astronauts eventually to Mars. But Artemis is so much more than that. And there's so much that goes into engineering Artemis, but I'm going to let this video do a better job of explaining that.
Between 1968 and 1972, America launched 9 human missions to the moon, 6 of which successfully touched down, allowing 12 men to walk on the lunar surface. NASA's next chapter of lunar exploration, called Artemis, has the task of not just going to the moon to create a long-term human presence on and around it, but also to prepare for ever more complex human missions to Mars. In short, everything we must be able to do here, we must first do here. So, what will an Artemis mission look like? Everything is designed and tested with our most important element in mind, the astronauts. This is their deep space, human-rated spacecraft called Orion, built in 3 parts. The crew module, where up to 4 astronauts will live and work throughout the flight. The service module, with life support systems for the crew and its own engine and fuel reserves. And a launch abort system, with engines capable of pulling the crew module to safety during launch should anything go wrong. To accomplish the task of launching our crew and heavy payloads, NASA is building the Space Launch System, comprising of a cargo hold, an exploration upper stage, a massive core stage, and 2 extended solid rocket boosters. Altogether, this is the world's most powerful rocket, and it exceeds the legendary Saturn V of the Apollo era in numerous ways. Sitting on the launch pad, the entire rocket, fully fueled, weighs just over 6 million pounds, 5.2 million of which is just the fuel. Once ignited, there is no stopping what comes next. All 4 RS-25 engines and the 2 solid rocket boosters come to life, thundering our crew upwards. 2 minutes after ignition, the solid rocket boosters are spent and released. 8 minutes after launch, the core stage is depleted and separated. The upper stage fires briefly, placing Orion into a parking orbit around the Earth. Here, the crew reconfigure the spacecraft and check systems to confirm everything is ready for deep space travel. With a go from mission control, the crew reignite the exploration upper stage engines to leave Earth entirely. The exact timing of this maneuver is critical to reach a speed that can escape Earth's gravitational pull, but also put Orion on a course that will intersect the moon days later. Once this burn is complete, the upper stage of the SLS is jettisoned and the crew aboard Orion coast for several days toward all that awaits them at the moon. Approaching the moon, we see the fundamental differences between Artemis and Apollo. Instead of requiring Orion to serve as an expendable lunar command module or to carry a constrained lunar lander, the Artemis missions will take advantage of a different approach, pre-staging. Everything needed for lunar missions will be positioned in advance by commercial and international partners. This includes rovers, science experiments, and human-rated systems on the surface. But it also includes a dedicated lunar station in orbit around the moon called Gateway. Here at this station, we can pre-stage a robust lunar lander and establish a strong communications relay. Designed with open standards, the Gateway can be expanded as new missions and partnerships develop, allowing multiple human missions on the moon at the same time and enabling ongoing science to be conducted even between human missions. The Gateway is also capable of adjusting its orbit to allow access to every part of the moon, something the Apollo missions could not do. But the real key in this approach is placing Gateway in a unique halo orbit to perfect the maneuvers needed for Mars missions. And with the growing list of commercial and international opportunities, Gateway is the ideal hub between Earth and all that lies beyond. Returning to our crew as they approach Gateway, the Orion must match the elliptical orbit of the station in order to successfully dock. Once on board, pre-selected crew members transfer to the lunar lander, while those assigned to Gateway remain on station. The lunar lander system itself is built for 3 unique steps: descending from the halo orbit of Gateway down to a low lunar orbit, descending from low lunar orbit to the surface, and once the lunar mission is complete, launching from the surface of the moon and ascending all the way back to the orbiting Gateway. Once back aboard the Orion spacecraft and undocked from Gateway, the crew fire their engine once to break out of the halo orbit and once again to sling the spacecraft around the moon, placing it on a multi-day trajectory back towards Earth. As they near the end of this journey, the service module is released and the crew module is oriented heat shield first. Entering Earth's atmosphere at 25,000 miles per hour, the friction of air slows Orion considerably, while also subjecting it to temperatures of 5,000 degrees. With the Orion now at just 300 miles per hour, a series of parachutes uniquely tested and produced for this moment deploy, decelerating the craft to just 20 miles per hour for splashdown. With each successful mission, Artemis ushers in the next wave of men and women to explore our moon and prove that together we are ready to go beyond.
So that was pretty cool, right? I think so. Next slide, please. As you just saw in the video, Artemis is a massive undertaking and a very complex mission. It also is a multi-phase mission with 3 phases of Artemis in the works right now. Artemis 1 is scheduled to launch this year. It will be an unmanned flight to test the Space Launch System and Orion spacecraft together. Artemis 2 is targeted for launch in 2022, and it will take the first crewed flight test to the Space Launch System, Orion. Artemis 3 will land astronauts on the moon by 2024, and about once a year after that. The video explained all the complex elements that are being worked for the entire Artemis mission, and you can see those 60 elements here. Today we're going to focus on the areas within 2 of these, and specifically areas where my team and I are working and engineering for. The 2 elements we will focus on today are the Space Launch System and Gateway. And we will dive even deeper into both of them and look at specific areas where my team and I have been working. Next slide, please. So let's talk about the Space Launch System. In the video, you saw that the Space Launch System, or SLS, will consist of 4 main components: a cargo hold, an exploration upper core stage, the core stage, and the solid rocket boosters, all together making up the world's most powerful rocket. One of the main components of the SLS are the 2 solid rocket boosters that will provide the power to get the rocket off the ground and out of the Earth's atmosphere. As noted in the video, the boosters will do this in just the first 2 minutes of launch before being spent and released, actually disconnecting the core stage so that the rest of the SLS can continue its journey and deliver our astronauts into the Gateway. These rocket boosters are what some of my teammates in Utah, Florida, and Alabama are engineering today, and they are doing some very important and really cool work. Next slide, please. So for the rocket solid boosters, our engineers are creating and updating technologies and materials to make sure their boosters meet the high demands and requirements for the whole system. It is, after all, the most powerful rocket NASA's ever built, and these are the largest solid rocket boosters built for flight. The 2 SLS solid rocket boosters are engineered in 3 assembly groups. My teammates in Utah work the entire boost cycle, from the forward assembly, the 5 booster assembly segments, and the aft assembly. In Florida, they do the heavy lifting on the forward and aft assemblies. From this top-up picture, you can see how complex a single booster can be, and each area requires special attention and conditions. The boosters alone are massive. At 177 feet long, each booster is about as tall as the Leaning Tower of Pisa, and each booster weighs 1.6 million pounds. That's to weigh about 4 blue whales. Pretty cool. I think so, and I'm sure you do too. The job of the boosters is to provide majority of the thrust or the force to get the rocket off the ground and make its way into space. They have a big, important job. As with any engineering project, there's a lot of testing that takes place, especially when creating something so large and complex. One of the coolest tests that we do are static fire launch tests. Static tests are full fire tests, meaning that the rocket is ignited and the propellant inside the booster is burned for the full duration, exactly as it would during actual flight, for just about 2 minutes. For a test, though, the booster is secured horizontally instead of vertically. We do these tests to help us gather data and information about how the motor is performing before it actually flies. It is a very important milestone for our rocket motors. Not to mention, it's awesome to see these tests happen in real life. In fact, our booster team completed a full-scale booster test for the SLS rocket last September. Let's watch a quick video from that test.
5, 4, 3, 2, 1, fire. T plus 5 seconds. T plus 10 seconds.
Activate head and CO2.
Activated.
Activate quench tool command forward and aft CO2.
That was another cool video, right? Yeah, I agree. Next slide, please. Now we're going to switch gears a little bit and talk about another part of Artemis that my Northrop Grumman colleagues and I are supporting right now. It's called Gateway. If you remember from the first video, part of Artemis pre-staging includes Gateway, a dedicated lunar space station that orbits the moon. Gateway is very critical to the Artemis mission because this is what will allow our astronauts to explore the moon for extended periods of time. Gateway is also necessary for future deep space missions like going to Mars. The Gateway outpost is where the Orion spacecraft will dock with our astronauts on board, and this is where the lunar lander will be pre-staged, ready to land the astronauts on the moon. Now, there are three critical elements of Gateway which provide support for long-term human missions to the moon: the Power and Propulsion Element, or PPE, the Habitation and Logistics Outpost, or HALO, and the Logistics Module. Today, we are going to focus on number 2, the Habitation and Logistics Outpost, which I will refer to as HALO going forward. Next slide, please. So, HALO. This is a really cool part of Artemis that my teammates and I are engineering today. HALO is where Artemis astronauts will live and spend their time. It will basically be their home while on Gateway. Its main purpose is to provide basic life support needs for the astronauts, supporting 4 astronauts for up to a month. HALO also has a lot of other important aspects, which are outlined here, but I won't go into that right now. What's important to know, though, is HALO is being designed for all these important capabilities right now. There is so much that goes into designing and engineering something as critical as a space station. Next slide, please. So I'm sure you all are wondering how we're going to design the HALO. This picture coming up now is a picture of one of our Cygnus spacecrafts. I worked on Cygnus for going on almost 10.5 years. I started on Cygnus my very first day here at Northrop Grumman, so I can tell you how amazing the spacecraft is. The Cygnus spacecraft is used to carry crew supplies, spare equipment, and scientific experiments to the International Space Station. And these missions are called resupply missions. I could talk to you literally all day about Cygnus because Cygnus is like my baby when it comes to spacecrafts. But what does that have to do with HALO exactly? Cygnus provides a number of advanced capabilities when it is completing resupply missions, and the HALO design is based off of our Cygnus spacecraft. HALO will be taking Cygnus technology to the next level. Since Cygnus is an unmanned mission, HALO has to incorporate environmental controls and life support systems to design to keep astronauts safe and comfortable during these long moon missions. Next slide, please. So right now, personally, I do not know how HALO is going to look or how it's going to be designed, but this is where I want to get you guys to get creative and innovative and think about how you would design your own HALO. Keeping the following in mind, I want you to design your own HALO. HALO is about the size of, let's say, a studio apartment, or maybe the size of an RV camper. For reference, the International Space Station is about the size of a 4 to 5 bedroom house. So Halo will be a lot smaller. Halo needs to be designed to be living quarters for up to 2 people at one time. This includes space to eat, sleep, lift a little couple weights, play a little Xbox or something, and just hang out, talk about whatever they want to talk about. There will also be a dedicated storage area where they can keep all their science experiments and any other experiments that they may have to do. Next slide, please. So here are your instructions, along with my email, where you can submit your Halo designs. But you can also email me if you have any questions along the way, and I'll do my very best to answer them. But now we have some time where I can answer some questions you all may have, either about the Halo Challenge, Cygnus, or anything else that you may have questions about. To ask a question, just click the Q&A button on the Zoom screen and type it in. And my good friend Emily will read the questions out loud.
Thanks, Darnell. And thank you for everybody who joined the call. Emily is going to look through the questions that are coming through and read some aloud for Darnell. We also have some of Darnell's teammates on the line who might be able to help him answer some questions. And they've been helping answer some questions in real time during the presentation. So Emily, as soon as you're ready, go ahead and get started with the Q&A.
Thanks, Paige. We do already have some questions queued up. So our first is from Seth, and Seth would like to know, when did you know you wanted to do this as a career, and how can I be like you?
That's a really good question. So I knew that I wanted to be an engineer at an early age when I was about 10 or 11. My mom bought her first Nissan Maxima back in like the early 90s. And she came from a Toyota Corolla that she had for since I was born. And that car has so much technology, and it kind of turned me into a car enthusiast where I was interested about how engines work, how suspensions work, how all these, electronics and stuff work. And that kind of, pushed me to want to be an engineer. As far as space and becoming, working on NASA and stuff, I kind of fell into this career. Two of my other colleagues that I went to college with, one is from this area, and he worked for Office Movers. And he helped move in a bunch of office stuff for what we were back then called orbital sciences. So he thought it was an interesting place, so he applied, he got hired, then I got hired, and literally the rest is history. I've been loving it every day since then. And I mean, just for you, I would just recommend finding what you're interested in, and like me, just go to college for that. I mean, that's the easiest way to know what you want to do or figure out what you want to do.
Thanks, Darnell. This actually follows that pretty closely, and it's a two-part question. One from David and one from Vincent. How much schooling is involved in being an exciting career like you, and did you join any clubs in college that helped you along the way?
So how much schooling is involved? I went to school for 4 years. I graduated, and I've taken some additional courses. We have a course here called the Space Academy, where we learn more in depth about satellites, rockets, etc. And I'm also trying to work on getting some more certifications and eventually get my master's in engineering management. What was the second part of the question? I'm sorry.
Did you join any clubs in college that helped you along the way?
Actually, I did not join any clubs in college. I did. I was in NSBE and IEEE, which is the Institute of Electrical and Electronic Engineers. But I had a full-time internship with the USDA, so that working school and between NSBE and IEEE, I didn't really have much free time outside of that.
Now, you said you started with an internship. Hayden would like to know where you can apply for internship opportunities at Northrop Grumman or learn more.
Oh, that's a really good question. So if you go to our website, I think it's ngcareers.com, there are internships listed there. And I highly recommend everyone who are in college or want to start college soon, to start applying as soon as you can. We have multiple sectors, multiple, disciplines. So there's a lot that, for an intern that you can do here at Northrop. And personally, too, I am a mentor for our interns. So you probably could be a mentee under me one day.
Julia would like to know, have you always wanted to work at Northrop Grumman?
Sure. I kind of fell into working for Northrop. We were, again, orbital sciences before, and then we ended up Northrop Grumman a few years ago. And so, yes, I would say yes, because I was orbital and then we're now Northrop. So, yeah. And Northrop has been great. A lot of opportunities. They've been introducing us to more, avenues of space and doing more creative satellites like our mission extension vehicle and some of our communication satellites. So, of course.
Awesome. Caroline would like to know, what technical skills should a younger person acquire to take a similar path to you? CAD, perhaps, or programming?
All of it. CAD, programming, electronics, mechanics, quality control, design. Anything. If you just think about anything that deals with space, thermal. We literally have, even finance, you really have every aspect of college can be applied here. I mean, we have to buy stuff, so we have to have people who are financially responsible. Everyone that works with me, we know how to use DMMs and, oscilloscopes, know how to read schematics, drawing diagrams, building stuff. I mean, growing up, I was into Legos. Now, practically helping build satellites. I mean, so anything that you can think about under the sun can be applied here because there's so much that goes involved to keeping people safe when we send, satellites to the moon, and even testing on the floor. A simple mistake can mess up a whole entire satellite. So everything you can think about can be applied here.
Awesome. Taryn would like to know, how long is each electrical component tested before being integrated with the spacecraft?
So that varies depending on the type of satellite, whether it's a GeoStar 1, 2, or 3, or our Cygnus satellite. Like, for instance, since we're talking about HALO, I'll talk about Cygnus. One of the main units on the Cygnus spacecraft is called a CAU, or Combined Avionics Unit. It takes us about a week and a half to test one unit because we have to do a continuity isolation check to make sure that all the circuit cards in the unit are tied together properly and that nothing is shorted out and everything before applying power works. Then we perform a electrical verification test to make sure that it works based on the software that was developed by our software engineers. And then after that, that's when we go into our environmental testing. We perform vibration testing, which is 3 axes, X, Y, and Z axis. Vibration testing is pretty much what it is. We put on a big vibration table and we shake the box to make sure that we want to implement liftoff and that the unit can survive. Then we go into thermal testing, which will put the unit through temperature the unit will see once it goes to space. And that is unpowered for 8 cycles. After that passes, we then go into thermal vacuum testing, which we put the unit through the temperatures and the space, the pressures that the unit will see when it's in space. And that takes about 3 days. Thermal is about a day to 2. So about a week and a half for one unit, depending on, that's just one. So, and we do a triple redundancy with Cygnus. So every unit, there are 3 parts that are identical, just in case if one were to fail, there's a backup and there's a backup for the backup.
Thank you. Brooklyn has a great question. Brooklyn would like to know, do people make parts for these satellites in different states and send them to where the project is taking place?
Yes, Northrop has a lot of suppliers, but I mean, I'm not supply chain, so I really don't know where everything comes from, but I do know with our other group upstairs, I work closely with another manager up there, Tracy Giza. She works with all of our planners to, organize the parts, secure them, order them, and just put them all together and make it work.
And that is what you guys are best at, is making it work. Eric has a good question. Eric would like to know, what is the hardest part of your job?
The hardest part of my job, that's a good question. So the hardest part is, I don't know, probably, I don't know, I gotta think about that one. I guess just, I don't know. You really saw me on this one. I never really thought about the hardest part, but I guess if I had to give an answer, it would be when a unit fails, or a part is on the spacecraft and then we have to come back, trying to make sure that we fix everything or find issues as soon as possible, and keeping the schedule on track, because we don't want to risk losing too much time or delay anything, because getting satellites, especially Cygnus, to the space station is critical, because our astronauts rely on us, because they need their food, supplies, games, pictures from their families, or anything that you could think about. So getting through errors quickly and efficiently as possible and preventing them from happening again can sometimes really be a challenge. But we've done a great job doing it. I work with great technicians and great engineers and great planners. So when issues happen, we do our best to, keep things moving along.
Absolutely, because things happen and you have to be able to roll with the punches.
Exactly.
Anthony asked a question that is an excellent follow-up to that, which is, what inspires you to not give up and keep trying until you succeed?
This is a really good question. And so my passion comes from two things. For one, where I grew up, working for NASA is unheard of. So for me, being representation for those who are from where I'm from or look like me, that is my passion. Number two, getting to this point of my career or a part of my life wasn't like a walk in the park. It was hard trying to find exactly what I wanted to do, find something that made me happy, and made me feel valuable to not only like my friends and family, but to everyone. Coming to work and like, we joke around, and especially like in my group and some other groups, that we're like the Brady Bunch. Like we work together so much. So coming to work and being around each other all day, every day, it may sound cliche, but we are like a big family up in here. So that's like my passion, coming here and hanging out, laughing, having a good time, and then watching the satellite go into space and knowing that I've had a part of this and getting to share it with the world is a passion.
Thank you so much for your time, Darnell. We have time for one last question for you, and then I know you have a lot going on, so we'll let you go. What are the daily responsibilities of your job here at Northrop Grumman?
So my day starts dark and early. We try to arrive to work between 7 and 7:30. So as you all may know, Northern Virginia traffic is not the best. So we fight traffic to get to work. I come in, I have a daily 9 o'clock meeting with my manager and some other program managers. We discussed test flow, test priorities, what's in test, what issues we need to resolve. And then after that, I immediately go to my team. We go over what we need to do for the day, who's doing what. And literally after that, it's meetings about test issues, meetings about any change that need to be made to procedures, software updates. If we have failures, I'm very hands-on. I like to go to all the meetings to know how I can help, how I can, help my team members, how they can, help me get through the day. So every day from start to finish is like busy all day. And then we try to squeeze lunch in sometimes. Sometime along the day, we eat, drink water, stuff like that.
Occasional lunch and an occasional rocket launch. That sums it up for Darnell.
Pretty much.
Well, thank you so much for your time today. I want to draw everyone's attention back to that Design a Halo challenge. So be sure to take some time at home with whatever tools you have on hand. You can draw it, sketch it, make it on a computer, on your iPad, make it with Legos. Just go through a reminder of how big it is. Make sure you fit all of the requirements that we lined up for you. Take a photo or a video and send your email to darnellstem@ngc.com. And we will take a look at all of those submissions that come in. Darnell's going to select his favorite to be featured on our website. And you can also send any questions that we did not get a chance to answer today to that email. So again, that's darnellstem@ngc.com. Thank you all today for participating with us and in all of our eWeek events. That concludes today's presentation, and we hope you all enjoy the rest of your day and have a great weekend.
Thank you, guys.